All right, folks, have a seat, get some dumplings. Thanks for coming. I'm going to quickly introduce Daniele and his talk, and then hand the ball to him. So it's my pleasure to have Daniele present the work that has been doing since essentially has come to visit my lab back in, remind me, July. That's right. So Daniele is a visiting scholar. He is pursuing his PhD in University of Naples, Federico in Italy. He's also affiliated with the University of Padova. And now one more affiliation, Boston University. So has been visiting here. And his advisor was also online, Marcello Cinque. He's the person I have to thank for having this collaboration. Okay, can you hear us? Also people online?
Yes, perfectly.
Fantastic. So interject at any time, right? Because I may not know what I'm talking. No, but Marcello is also the person I want to thank for this collaboration to happen. And today we are around at the end of his visiting period. It's sort of the coronation of the work he has been doing since July. And so he came here with one burning question, perhaps more than one, but one big question, which is, we're trying to build a very complicated system. At least I'm doing my part to build a very complicated system. I don't want to spoil anything. You will give you details. How the hell we organize computation to solve this goddamn challenging problem in a way that one day it can be scalable, cost-effective, and we can solve this problem for humanity. All right. So again, he will tell you exactly what that problem is. But without further ado, please welcome Daniele.
Thanks, everybody. Okay, so I can start. You see, the name of this project is the Omnivisor, a word that can remind you, the one that probably everybody here knows, that is hypervisor. Okay, I want to start by present myself. Well, Renato already did it very well, but just a fast recap. Well, I've studied at the University of Naples, where I took my computer engineer, a bachelor and master degree, and then I started my PhD student enrolling in this program called Fusion Science and Engineering. Yeah, actually, I'm doing this PhD willing to solve problems in computer system, of course, that can help the fusion science. And well, now I'm here as a visiting student, as a visiting scholar, at BU with Renato at the Cyber Physical System Lab. So I want to introduce this presentation with nuclear fusion. Well, something that you don't expect here. I think maybe you can be interested in it. Well, real fast with this nuclear fusion. Well, nuclear fusion is the process that happens in the stars and our sun and produce energy through the union, actually fusion union, of two nuclei that are deuterium and tritium, isotopes of hydrogen. These unions of deuterium and tritium form another nucleum called of helium, and during this process we are going to lose 0.02 of their mass. Of course, this mass is not real lost, but is converted to energy using the Einstein law. Well, this kind of fusion reaction is very energy effective. You know, the reaction yields 17.6 mega electron volt. That translated is, okay, taking 1 kilogram of fuel, you'll have 676 units, where 1 unit is the energy used by 1 US citizen in 1 year. So with only 1 kilo of fuel. Well, that's great, right? Well, also, the deuterium is very abundant material in nature because it's an isotope of hydrogen, right? So that's good. Well, the problem is that this kind of reaction in the stars, it takes a great pressure and temperature to happen. We don't have that pressure here, so we need a lot of temperature. We need hundreds of millions of degrees to make the fusion happen here on Earth. and that's very challenging. And there is another problem that 80% of the energy generated is in the energy of the neutron that is generated during the fusion. You see, there is the medium items and the neutron. Neutron particles are not easy to manage, and it's not easy to take back the energy from the neutron. So this is another problem. And the final problem is that the tritium, this is another isotope of hydrogen, is more difficult to obtain with respect to deuterium because it's not, you cannot find it in nature. So we usually take him from lithium by breaking the lithium. So there are a lot of pros in doing this, but it's very challenging. Well, how can we try to produce nuclear fusion on Earth? There are several techniques. The one I want to talk to you about is the magnetic confinement. Well, what we can talk about is tokamak-based reactor. Tokamak-based reactor are this kind of reactor which try to confine in this, we can say it's a sort of donut shape, toroidal shape, with inside a gas full of deuterium and tritium, and we want to heat up this gas to hundreds of millions of degrees and confine that in order to not let it touch any boundaries, because any kind of material at that temperature is going to melt, right? So ITER is the world's largest magnetic confinement plasma physics. I've been there actually, and as you can see, this is the dimension of just one of the coils that comprehend the reactor. So it's quite big. And well, the purpose of this machine is only to prove the possibility to create fusion reactor and to do electricity on it. But actually, it's not going to be really connected to produce electricity. It's just a scientific project. And the goal is to produce 10 times as much thermal output power as thermal power absorbed by the plasma. The plasma is the gas I told you about, but since it's electric charged, it's called plasma. Well, okay. I think I introduced you the concept of nuclear fusion. What I want to tell you is that, of course, this complex machine is composed by different plant systems, more than 30. Plant system like cryoplant system, because the magnets are superconductor and that to be at almost 0 grade, at 0 grade. So very cool. And we need the magnetic system to work to confine the plasma. We need the heating system to heat the plasma, and so on. There are a lot of systems. All these systems produce around 1 million of signals that have to be managed in order to control the machine. Well, to do it, there is this control data access communication system, CODAC system, in the ITER project. That is the brain of and the central nervous system of ITER, and basically connect all this system using a computer networks. And the CODAC system have to do several functions, starting from plant operation and monitoring through operation scheduling, time and synchronization, and data access. So this is a complex machine, and each of these systems is complex itself. But if we try to make it simple, at the end, a system as the magnetic system, that the one I work on, is a cyber physical system, right? So we have a machine, physical system that we have to control with computational elements. So we have a bunch of computational elements that take inputs from the machine. So temperature, the oils, current, the current of the plasma, etc., collaborating between each other and produce output as control output to the machine to control. Right. Now, computational elements usually in this cyber physical system are simple microprocessor that does little stuff, right? So single application, a single microprocessor, hundreds of microprocessors that do stuff, send data to through the network for further analysis to servers and go. What's happening is that we are trying to approach this kind of problem through an integrated development rather than a federated one. Yes.
So just a quick question. So in such an environment where you have a very physically stable place, right? This is not a car moving. This is not a rocket ship launching. It's
Yep.
not a fighter jet going.
Yep.
Why is the natural, quote unquote, correct or natural architecture one in which there's so much distributed computation versus the trade-off between bringing it through a high-speed links to a more centralized computational infrastructure?
What's sorry, could you repeat me just
So I think you were implying, right, that this system
Mhm.
is got lots of microprocessors
Yeah.
distributed. I'm assuming those are distributed closer to the sensors.
Yeah.
But why is that in such a highly constrained environment the right approach, opposed to bringing more of the signals to actually a central computational system?
Okay, basically because of, well, yes, the principal approach is to use several more complex systems to resolve the problem. So if we take the machine, of course, we want to calculate the specific parameters to solve the problem. Yeah, to understand which kind of signal to send back to the machine to control it, right? And this says, okay, maybe you can just use very complex and powerful servers to do it near the machine, right? But actually, there are several, let's say, millions of signals that have to be managed singularly. Then the union of this signal that are pre-processed usually in this microcontroller are then sent to servers that does the computation. What's happening is that since it is a very new research project, what's happening is that the application is going to evolve years by years. And so what they need usually is to have something that is capable of executing this kind of new application before going to the server for further analysis or more complex algorithm. Fact is that the number of applications is very heterogeneous itself. So there are simple applications that can be actually executed on this kind of simple microprocessor, and other machine learning application or very hard computational application that have to be on server. Now, of course, microprocessors are near the machine. So what we need is to do something a little bit more complex near the machine that has not the time to go to a server and go back to the machine. So it has to be solved in a very quick way. We are talking about kilohertz of frequency.
So what was it? What was the frequency?
What?
Sorry, could you repeat the frequency?
Yeah, kilohertz.
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 Yeah. So, okay, I'm just going to assume that the math all works out, because so I've seen some very big projects in the past where the trade-off was made the opposite direction. So if you consider not just commodity servers, but you consider something like a blue gene architecture with very high-speed I/O links and other aspects. I'm just curious, was it somebody's assumption and cost benefit analysis that led to this? Or is it actually, like, scientifically, there is no technology that makes the right trade-off between having the flexibility, because once you do have it centralized, the flexibility actually of multiple applications is actually in some sense easier because you don't have to deal with all the heterogeneity. So that's why I was just curious whether it was somebody's principal who said, so like, this is what I think how it should be done, or is the math of technology saying, no, this has to be done with this architecture?
Actually, it has been, to be honest, a process, right? In the first place, this kind of controllers have been done only on powerful machines. Starting from that situation, what happens is that we found out that there were some algorithms, some application that could be executed faster if executed on a microcontroller near the machine. And we didn't need to put this kind of application on a server on a more powerful machine. And so we started doing that. Then this kind of application becomes a little bit more complicated. Maybe they need an accelerator, an FPGA or a GPU. So what they think, okay, just replace these microcontrollers that cost a lot, few dollars, with multiprocessor system on chip, that the one I was talking about here, that are $1,000 machine, but are still embedded systems somehow, but they have on top accelerator like GPU, like FPGA. So this kind of application that we don't need to execute on a powerful HPC processor. We can execute on this stuff. So let's do it on this kind of processor. That's the idea. I hope I
Yeah.
Thanks. So the reason why usually we try to bring the application, multiple application on this kind of microprocessor is to reduce the size, the weight, and the power, and the cost of our hardware. So instead of having hundreds of microcontrollers, we use few application on this multi-processor system on chip, powered with multiple processor, accelerators, and etc. But there are some challenges that have to be considered in this situation. Principally, the isolation, the temporal isolation of application. Because if we have multiple application, maybe with different criticality of the same microprocessor, on the same, MPSoC, what happens is that the execution timing behavior of the application can be corrupted somehow, can augment, caused by other applications of the same system. And that's a problem. And the other problem is the complex of the heterogeneity of this multiprocessor system on chip that present, as I said, you different kind of processor, with different instruction set architecture and accelerators. Well, what is the solution in the fusion until now? Well, the solution is that, okay, taking the magnetic control system problem, we want to take the plasma position, saying, okay, the plasma in this moment is in this position. We want to power the coils with a certain current to maintain the position stable. Well, how we can do it? We need to do high frequency controller to manage the plasma shape, kilohertz of frequency. Okay, we need other application. For example, we need to understand through a machine learning algorithm, which is we want to forecast the machine breakdown, to understand when the machine is going to break actually, to prevent this and do some kind of action to prevent it. And finally, we need to take some data. Usually one experiment produces terabytes of data and save them in order to further analysis, future analysis of the situation. Well, what's happening if the kilohertz frequency controller fails? Well, it's not going to explode like a fission or something like that, but there is a big problem. The moment in which the plasma is going to bump into the coils and maybe breaks one of the coils, what happens is that these coils are very costly. You're going to need to spend a lot of money to substitute it, and not only money, but also time, because if you have to rebuild the reactor, it's gonna take also years to do it. So we are not going to do experiment for years, and this is a big problem.
So like, could you describe like what is it doing to the coil? Is it just moving them, adjusting?
No,
its position?
it's just the current that we give to the coils to control the shape. If I want to be a little bit more precise, we have three kinds of coils that are the inner colloidal field that gives energy, like to the plasma to heat it up. Then we have this toroidal magnetic field that control like the shape in somehow, but not the shape in the sense of vertical shape, but just okay. And then we have the poloidal field that instead, for example, control the vertical shape of the plasma. So the union of all these magnetic coils powered by our controllers are able to maintain stable the plasma inside the tokamak.
Have you ever seen those levitating plants?
Yeah.
Do that, but with the plasma which is hotter than the surface of the sun and on 3 dimensions.
So the problem here, okay. So we are going to put everything, all these three applications in this example on a single board. Well, no, this kind of solution is not accepted yet. And the current solution is over-provisioning. Okay, we have 3 applications, we are going to buy 3 boards. Of course, this is okay for now because this is an experimental machine and we are trying to make it work. But of course, there is a lack of scalability in this approach, right? Because this is just 3 applications of magnetic system, but there are 330 systems. Each system has a lot of application. If you are going to buy several boards for each application, is not going to scale very well. So,
And what's interesting is that they're so concerned about temporal interference, so the temporal behavior being corrupted, that they throw away any layer of OS, even like even simple OS. They go full bare metal. They turn off caches. They try to make it as predictable as possible. They strip everything out because they don't trust anyone.
yeah, so they are going to execute bare metal code on, for example, one single core and using one accelerator on a board that maybe has several cores, several accelerators, stuff like this.
But from
Of
that
course,
perspective, the code that's actually running, how much of this looks like, control theory loops that fundamentally, they might as well be fabbed into the hardware. And the only reason we're doing this is because we haven't figured the parameterization and the algorithm quite out yet. Because I would imagine that the long-term design of such a thing, one hopes that at least the whole point of the near computation to close to the device is very much control loop-like.
yeah.
So in which case, wouldn't this just simply be justified as the way that you evolve those algorithms? And then you say, okay, afterwards it's going to be more or less burned into firmware, or actually maybe even further than firmware, custom circuit.
It's the divide between you want to do it or you want to do it well. Yeah,
Yeah, exactly. Yeah, I think there are, as I said, this is a research project. So it starts from controller that are very similar as you imagine to the classical theory of controllers. Going through last year in Nature, is gonna be there have been a publication about reinforcement learning used to control the class. So really, there is a bunch of kind of possible solution for this controller, and they are trying to find out the best solution for it. So there is not yet a best solution.
Right.
And so, well, okay, so this is the current solution. What we can do to improve this? So let's look the hardware as it is. A possible solution to do this kind of isolation of application, so mixed criticality on a single board, is the use of embedded system virtualization. So just a brief introduction about traditional virtualization. Probably everybody here already knows that hypervisor is a software layer that abstracts the hardware to virtual machines so that multiple virtual machines can run together on a single board, right? And this multiple virtual machine has a good resource utilization because it is the hypervisor that manage it and make it run in the right processor with the right boundaries in order to improve the resource utilization, improve the flexibility so you can run virtual machine, power down, and so on. This is traditional virtualization. The problem here is that, okay, we can do it, but at what cost? There are high interferences between virtual machine, predictable interference that avoid the possibility to have real-time guarantees. So we don't have real-time guarantees with traditional virtualization. So what is going on in research now is people are going through real-time virtualization. There are several kinds of real-time virtualization, but the one I want to focus on is the simpler one, I can say, that is static hardware partitioning. So this kind of hypervisor just take the hardware and statically divide the hardware resource for each virtual machine. So a virtual machine has a pin, for example, CPU, and there are specific memory area that can access that are not accessible by other virtual machines. That's static hardware partitioning. That's great because we can have reducing interference between virtual machines, very good, very low latencies that have been proved by recent works. And we have also minimal cost, minimal code base. So in theory, these hypervisors are easily certifiable. There are static partitioning hypervisors that are certified. But the problem, of course, is that it's less efficient of using traditional virtualization, but, well, it's better than using a single board on a single application. That's for sure. Well, there are several static partitioning hypervisor currently in use in several projects and stuff. But the question that we figured out is, okay, but can static partitioning hypervisor, as it is, deal with the heterogeneity of these multiple system chip we are talking about. But to reply this answer, we have to look the multiprocessor system on chip. How the multiprocessor system on chip is done? Well, I brought you here an example of a specific board. In this case, it's a Zinc UltraScale Plus from the Xilinx. And well, if you look at it as is quite complex, okay? It has a lot of stuff inside, but we can analyze it more deeply. So usually what we are interested in a core, the first thing we look at is the processing core, right? The CPUs. Here, they are named that stands for application processing unit. And they are the classical CPU we have in our PC or wherever. So they are complex in a way that they have complex technical stuff in it, like, for example, branch prediction. They have support for virtualization, so you can run operating system on it. And we can say that those are microprocessor level CPUs. But we don't have only APU on this board, but we have also microcontroller level CPU. In this case, what we call RPU, real-time processing unit. This kind of unit doesn't have branch prediction, doesn't have virtualization, are very simple. Very simple because they have to be as predictable as possible. They don't have a cache. They have only scratchpad memory, sort of programmable cache that you can use just to understand exactly which kind of information you need to have fast, and which kind of information you can have in memory, for example. It's very predictable core that can be used for hard real-time tasks. Yeah.
I just want to make sure I heard you right. So the APU, the application processor unit, can also run an OS there.
Yeah.
Presumably in
Linux, whatever. You can run an OS, you can run also an hypervisor. So specifically in this board, if you are, if you know this kind of ARM processor, there are a quad-core Cortex A53. So this classical processor we can find also in our smartphones, for example. Well, then we have also programmable logic, FPGA, on the same board that can be used to program some accelerator. Oh, sorry.
Sorry, maybe I didn't hear. Can RPU also run something like Linux, or is it much more stripped down?
No, the RPU in this moment cannot run something like Linux because they are very simple. Imagine like a microprocessor, so they don't have support for virtual memory, they don't have an MMAO, but they have an MPU, memory protection unit. So they don't have the translation from virtual to physical in hardware, but they just protect the memory through tables. Yeah.
And one more question: do RPU and APU, do they have access to same I/O? And if so, is there a contention between them?
FPGA too.
Okay.
FPGA too. Yeah, the problem actually is that if you see this scheme, all this processor unit going to the same DDR memory controller, going to the same I/O. So all the interconnection is very complex itself. There are a lot of mechanisms I want to talk to you about, but they share in somehow these resources. And so the FPGA, as I was saying, we can implement on it accelerator, but also other cores, soft cores. That's the name of cores implemented in FPGA. And all these processing units are going to share I/O, DDR, etc. So I want to generalize this scheme. So going through the communication between the cores and these resources. So let's do it. If you see, so these three typologies of CPUs, microprocessor CPUs, microcontroller CPUs, and programmable logic CPUs, they can communicate with the resources in this way, the memory and the I/O, through a series of layers that I'm going to discuss. The first layer is the address translation. So as I anticipated, the microprocessor CPUs has MMA. So you can do virtual addresses, you can work with the virtual addresses. What about microcontrollers? They don't have MMU, they usually have MPU, but not always. But the MPU does not enable the virtualization of addresses. And then we have the soft core and programmable logic. In that sense, soft core can be implemented in hardware with something similar to the MMU, but you have to do it basically. What usually happens is that you do a very simple processor to execute specific application on this FPGA. So you don't have usually MMU, but the FPGA itself is an I/O device. So it is powered with SMMU, what in Italy is called IOMMU. That is another way to do virtual to manage virtual addresses, right? This is from address translation, but there is another layer that is about temporal isolation, I call it. So ARM has developed this protocol and this hardware called quality of service that is used to manage the bandwidth limitation of the cores through the resources. So through this kind of hardware, you are able to say, okay, you CPU, for example, microcontroller C1 can send at most X messages at second to the memory. That's something that you can do with the QS, of course, with some limitation. Finally, then we have spatial isolation. Sometimes in this modern MPSoCs, we have also something similar to the MPU, so memory protection unit, that you can imagine as a table saying, okay, this manager in the system can access only this region of memory. This other manager in the system can access only this other region of memory. And this kind of MPU, system memory protection unit, or IOMPU, as you want to call, has this role. The SPPU is the same for peripheral, so system peripheral protection unit. This is another layer that exists in this board. So when you employ an hypervisor, what happens is the hypervisor creates virtual machine on the classical microprocessor CPUs. This virtual machine can access the memory, can partition the memory using the MMU. Okay, so you are sure that virtual machine between each other is not going to corrupt thanks to the MMU. But there's a lot of stuff in this kind of microprocessor, multiprocessor system on chip that are not touched actually by the hypervisor. There are some works that touch the QS. Lately has been discovered, has been tested, QS can be used for real-time purposes. So it is possible somehow to use this kind of mechanism to regulate the bandwidth allocation for several masters in the system and provide real-time guarantees. That's really good. But what we can do with the Omnivisor, that can be an extension of partitioning hypervisor, is to take control all over these kind of technologies and makes possible to create virtual machine, not only on microprocessor CPUs, but also on microcontroller CPUs, and also on soft core running on programmable logic. In this sense, we have to implement some mechanism to create temporal and spatial isolation. Spatial isolation because we don't want microprocessor controllers, for example, to access the memory of virtual machines running on soft cores or running on microprocessor controllers, the microprocessor CPUs. And at the same time, we want to guarantee temporal isolation. If I'm running several virtual machines on my microcontroller CPUs, I don't want them to give temporal problem, to augment the temporal execution time of application running on APU. So we want to achieve temporal and spatial isolation, and we want to do it in a transparent way so that a user can simply decide to run only a virtual machine. This virtual machine is going to run a specific core indicated by the programmer in a simple way. And the Omnivisor has to manage all these kind of hardware resources to make it possible, right? Okay. Of course, to run this kind of software, so to run an Omnivisor, you need a board that respects some requirements. First of all, it has to be multiple core cluster. That is true for several multiprocessor system on chip. It has to have the address translation, at least for microprocessor CPUs. Otherwise, it is impossible to run a hypervisor in it. It has to have some QoS-like regulation to regulate the bandwidth in hardware. It has to have protection for the resources, so SMPU or IOMPU, as I told you. And it has to have to give you the possibility to manage the power of the system. So to power on a core or power off a core, something that you can find in ARM-based and Intel-based processor as well. Okay, so this is what we want to do. We are done, basically. major part. And okay, I want to give you an example of how this is possible by a user to launch a virtual machine on a remote core. Well, a remote core, I intended it as whatever core that is not part of the microprocessor, so the one where the Omnivisor is running. Given a privileged virtual machine, so a PVM, that is a concept already known in static partitioning hypervisor, the PVM is the only one that can actually require the creation or destruction of virtual machine to the hypervisor. In this case, to the Omnivisor. So if the PVM asks the Omnivisor to launch a virtual machine or a remote core, the Omnivisor is going to load the image of the virtual machine in the right position in memory, in the right range of memory. It's going to configure an isolation level, an isolation layer to protect the virtual machines. So it's going to reprogram the MPU, reprogram the MMU, and program the QoS regulation mechanisms. And finally, it's going to ask usually to a firmware that is the only element that have a higher privilege level to power on the specific core. In this case, the core starts and start reading the specific code the Omnivisor has loaded in this memory, and is completely protected from access other resources in the system thanks to the Omnivisor. Well, of course, this is just an example, but the Omnivisor have a set of features that can offer to the virtual machine. Specifically, the interface to the PVM, so the privileged virtual machine, to give you the possibility to create, destroy, stop, and restart virtual machine.
So I just want to, maybe this is just a dumb question, but that VM isn't a VM. It's not virtual, right?
It's not virtual in the sense that there is not virtual translation of addresses, but is something completely controlled by the Omnivisor in the sense that
Right, but that doesn't make it a virtual machine. It's a partition. It's a partition machine or something.
Yeah, yeah.
It's just very strange to hear the word virtual machine referred to as creating a partition and running a physical machine there, which has a lot of much more powerful features. I don't think you should taint it by calling it virtual machine.
Okay, I understand
It's a compartment.
There has to be a better term, but it's not a virtual machine, and it's much more powerful abstraction you're building. I like this.
Okay, yeah, that's true. Actually, there is no translation of addresses, and so it is not a virtual machine in that sense. We call
it has unmitigated access to the resources it's granted. There's no mediation by the hyper or the Omni whatever the visor to that access.
Yeah, as a matter of fact, that it was that word unmediated. So in some sense, it's an unmediated machine, right? Because it's not just about virtual addresses.
Right.
The point is there is no decisions, protection, enforcement
On the
of
critical path.
policies on any of those critical paths of access.
Except, well, there is the quality of service.
That, but
Constraints.
also it cannot exceed its boundaries, the way.
Right.
No, okay.
But that is,
Whatever it assigned, yes.
yeah, but and that to anything that's assigned outside of the quality of service guarantees, it has unmediated access. And I think that's much more powerful and interesting than when you call it a virtual machine, it automatically adds this assumption that there's this mediation that's happening much more frequently.
Okay, yeah, okay, I understand. Yeah, actually, we call it virtual machine because it behaves like very similar to virtual machine in static partitioning hypervisors. So it is an extension of static partitioning hypervisor in the sense that virtual machine are completely the resources are statically assigned to this software.
Right, but they still have, in order to do that in a traditional system, you have to set the page tables for them. You have to, and you're controlling, and that's actually on the path, and there is a virtualization overhead to all that. Here, there's none of that.
Mhm. Yeah.
There is one clock cycle of overhead for the MPU.
Yeah. Okay. So
Low overhead.
But there is a translation that's happening from guest physical to host physical.
No, for these ones, no. they don't go through they don't have an MMU, they don't go through the SMMU, they go straight to memory. In fact, the problem is if you use remote proc in Linux, you know, that's the typical driver that people use to power to work with this kind of CPUs. Remote proc also does not set up any of the protection mechanisms. So if you launch a remote proc binary, that thing can completely destroy the entire system. There's no compartment. Even if that one is launched from within a virtual machine, then it's game over. So there's no
I
protection.
don't know what remote proc is.
Well, remote proc is a driver of Linux, which is used for handling, for loading binaries into coprocessors like this one, right? So there's many of these heterogeneous systems, like they have an M4 or an M0 on chip or an R5 like this one. And the driver that people use is the remote proc driver of Linux to load ELF onto those and launch them. The moment you do that, it's game over. That thing is the king of the system. In fact, they even bypass secure, non-secure privileges, right? They can act and access memories is also marked as trust zone secure, right?
Yeah, exactly. We had some example of this. So basically, if you use this kind of, if you use virtualization, static partition virtualization, and inside the virtual machine, you give access to the remote processor that is considered I/O at all the effect, you can, with that virtual machine, run whatever on this core, and the core is going to access wherever on the board. Also trust zone phases and accesses. So the very goal of the Omnivisor is to say, okay, you can run something, a software in this case, on a remote processor, but it's somebody that has to say, okay, but this code has not to access the other virtual machine, the virtual machine memory, for example. So you're creating a sort of isolation layer to block these cores to mess with the system.
Now, I guess in the case where it's an FPGA or software, you're still using the IOMMU to do that.
Okay.
Yeah, you can use IOMMU to protect.
The partitioning thing doesn't apply on the FPGA, right? So that you still have the translation going on.
Yeah,
So-
with if you use the FPGA, you can actually use the SMMU or IOMMU to use the other's translation.
But you have to, right?
You have to.
You can disable it, but yes, you can use it, right?
But there is no, if you go back to the mechanisms that you had, what were the mechanisms to give you the partitioning? It was,
You can also go through an MPU, right? You also go through an MPU from the FPGA.
so why wouldn't you want to do that? That would
You want to
give
use the SMMU? SMMU gives you virtualization and partitioning, but also you can also have a second layer of only privilege through the MPUs.
Right, so MPUs give you just the isolation,
Just as a-
but no translation. Is that good enough for most things, or do you need to use the IOMMU? So curious.
Well, it depends what you're trying to do. If you are, for example, if you run an SMP system, and one of the devices is the DMA synthesized on the FPGA, and you're now launching a VM that is using the DMA in the FPGA, ideally you want both of them to look at the same IPAs, right? So you set up the SMMU so that DMA sees the same intermediate physical addresses of your VM. That's what the SMMU is for. Does it make sense?
Right, so if there's any communication with the things running back on the
If
microcontroller,
they
then
see
you
the
have to
same
use that.
stars, yeah.
But for the native code that's running there and for everything else,
No,
all
correct.
you want is isolation, you don't
Correct.
care about.
If you just have an accelerator that works on its own,
Sorry for distracting everything, I just.
I mean,
Thanks.
these are all good questions because it makes, we were as well, when we look at it and say, why these things are here, right? Well, we're supposed to, why, what's the purpose of this? And yeah, I mean, eventually, you realize there are application scenarios where one or the other is needed.
Can you like change those isolations after you've already loaded up the VM like dynamically or?
Yeah. All the
Could you repeat the
mechanisms
question?
about are dynamically mechanisms.
Question was like, could you change the isolation dynamically after the VM was already loaded?
So actually, there was an interesting case where if you don't do things carefully, the RPU technically is a very privileged, right? So technically, it has access to the space of configuration of the MPU. And so, yeah, you can restrict it, but if you still give access to the configuration space of the MPU, the RPU can go in and change its own configuration.
So remind me what the
So you
RPU.
can limit that.
Real time.
Oh, yeah, the
Real
small
time.
microcontroller.
Okay.
Yeah, the Omnivisor takes care of that too, right?
Exactly.
Yeah.
So when the virtual machine is created and the MPU is programmed, if you launch a code on the RPU, what you do is also programming an MPU that disable the access from RPU to the MPU. That cannot change itself its permissions.
So exactly in that line, right, are we assuming all the VMs are being well behaved at least?
No.
For a minimum,
We are not assuming that.
for example, from PGA, you can fake that you have the highest privilege by playing with XI bits and then change all the QoSs, right? So who prevents
Basically, you can use this system memory protection unit and some memory and peripheral protection unit to avoid this kind of behavior, because this kind of protection units are imagined as near the resource to protect. They are not near the core as the MMU, but are near to the resource to protect. So, for example, one of the resources is the memory, but other resources in the system that are protected by the MPU are, for example, the full power domain switch, where there are all the registers to change all this stuff. So you can simply program this, this MPU, this memory protection unit, to avoid the access to a specific register, and so to avoid the FPGA to take control over the hardware.
My question is, what is being checked, right? So, for example, MMU, we have like bits, permission bits, right? So the QoS, does it look at the sender's address? It has hard
Stream ID.
The stream IDs, the ideals of the stream are
PGA
checked.
can fix the ID.
Not all of it. You can fix some of it,
Yeah,
but not the
Plus
top
6.
bits that are asserted by the SMMU. But yeah, good point.
yeah.
Normally you see the port as 6-bit ID, but actually it's 10, and the top bits are actually asserted for you by.
Exactly. So you understand who is the manager talking to you, and then you can activate the so-called, in this way, in the Xilinx jargon, it says poisoning of the. And okay, so what was the example that virtual machine start? We are talking about the features of the Omnivisor in that sense. There is a feature that is ongoing, we are working on, and it is about hypercode. You know that a virtual machine usually can, in some case, call some services of the hypervisor through hypercode. So what happens is if a remote virtual machine or remote CPU want to call an hypercode, well, we are trying to develop what we call the remote hypercode that is going to have the same result with, of course, a different mean, because you have to communicate with the Omnivisor through interrupts and shared memory in order to request a specific hypercode. And then that's the Omnivisor is going to take over and do stuff depending on the hypercode. But this is ongoing stuff. Well, the Omnivisor is going to give you dynamic reconfiguration of access permission. That was the answer, the question that answered the question you asked before about dynamic reconfiguration, and also dynamic memory bandwidth allocation. So QoS can be reprogrammed online at runtime to decide which kind of bandwidth you want to allocate to a specific virtual machine. Well, of course, in this sense, the Omnivisor has a set of responsibility too. In first row, we have to prevent the escalation of virtual machines privilege. If we intend the virtual machine as the software running on normal core and also remote cores, it means that the virtual machine running on a remote core cannot access, for example, the MPU register, because it cannot actually, it's not the right privilege to access the register, right? And not the memory area of other virtual machines. So the Omnivisor should prevent the escalation of virtual machine privilege and also prevent unexpected interference. So if I'm running a virtual machine that is high critical, hard real time, I don't want another virtual machine doing other stuff to interfere with that machine from temporal point of view. Okay, so just a couple of words about our implementation of the solution. we decided to use the JLAU's hypervisor as yeah.
So just before you kind of go into the solution.
Yeah.
What is the nature of the code that you're running in these, whatever, semi-VM thingies, that partition, should I think of it as just a simple controller logic, or is it essentially a application that comes in ELF that could do arbitrary things that has some interface of going back and getting functionality from the base operating system running on, like what is the complexity of the code that's running on that?
Okay, I think that depends on the specific core you want to use. For example, an RPU probably is going to execute a simple controller, as you say, or a real-time operating system at most, running several simple application, a controller doing by simple threads, in this case, tasks, we can say, a real-time operating system. And so, yeah, I can imagine that this kind of application is going to access often the memory and his cache to do this kind of control. Yes, simple application. But an example on soft cores.
5 minutes,
Okay.
maybe we should get to the results, because
Sure.
we also have results.
Yeah, sorry. Maybe on RISC-V on a soft core, you can implement something more complex depending on your needs. I'm imagining, for example, you need to create.
Wait, but you don't have, I'm just curious if you have any example. It sounds like you're not there yet. You're building up. That's fine.
We run benchmarks right now, the full suite of benchmarks. We run general purpose code, but nothing that right now uses heavily services from the rest of the system.
I can say, I can just complement, if you hear me, I can just complement to say that there are examples taken from the Fusion community where they are using the RPU to do real-time packet management and processing, and the application programming unit to do more complex stuff. And this is already done, but it is done completely manually. So yes, on the RPU, there might be drivers for high-speed networks or control loops running on real-time operating systems, yes.
Okay, but we're not thinking about, it's not doing TCP/IP over socket interface going back to the outside world. It's not, it's.
Oh, in one case, they are using lightweight IP without an OS directly on the RPU. Yeah, they've done that in the Ether, yeah, in the Ether machine.
We're also porting Marta, the full framework that does.
We are trying to port a specific framework used in Fusion reactors. It's called the Marte, and it is used to create real-time code. It's portable in different architecture and operating system, and basically helps the researcher from this community to create real-time code starting from MATLAB project, Simulink. So they do the controllers in MATLAB, and then they port it through this framework, so to create C real-time code and running on this machine. So we are trying to port this kind of code to run on different processor as virtual machine isolated on the board.
Yeah, because that's all the point I was going to make, because I suspect there might be what's done today versus what could be enabled, because what we found in the past is, of course, no, we'll never write it in Python, and then all of a sudden they want to write it in Python. But more importantly, what I was very curious about is typically the thing that gets overlooked is a lot of that code has to be audited and logged. And they often have to generate trace logs of all kinds of auditing stuff just in order to understand. So I'm guessing that all generates a much deeper demand than what is probably expected today.
Last note, and then I'll let you continue, but there's a it's a huge push for running WebAssembly, for example.
Yeah.
Go.
Okay. I'm going to go to the conclusion and to the results. So from the implementation point of view, we decided to use JLAUs for a couple of reasons, principally because it has very low differences, because it has already a ready-to-use implementation of the QoS mechanisms and on software bandwidth regulation, in this case memguard, and it's done by Minerva project. So reusing this kind of partitioning hypervisor gave us the possibility to focus on the other part of the system. So the QoS was already done. And as a hardware, I showed you the Zinc UltraScale Plus platform because it has all the requirements I discussed with you before. And so this is the launch of a virtual machine on a RPU or RISC-V on the specific software and hardware that we use. So as we can see, there is the QS, the XMPU, that are the Xilinx memory protection unit. So it's a specific system memory protection unit. And okay, as a result, the first thing that I want to show you is the boot times of these virtual machines. Specifically, we wanted to reply to the question, okay, if we have a mission critical, we want to do mission critical dynamic reconfiguration. What's the time to do it? So if a virtual machine fails, what's the time of rebooting them? So to do the boot of this specific virtual machine. If we do it with traditional, with normal JDAO, so a specific hypervisor on application processing unit, that's the scale. So hundreds of milliseconds. We change the image size, and we see that if we divide the boot times in 3 points, the creation time, that is the time in which the hypervisor just create the structures, remove the pool of resources to give to the other virtual machine. The load time, that is the time in which the image is loaded in memory, and the boot time is the time actually in which the CPU is restarted, or is started, or is taken out from reset. We have these 3 values. Of course, the creation time is independent of the image size, because it depends only on the resource to give. The image, the load time depends on the image size, because you have to load more bigger image in memory. And finally, the boot time is independent too. And these are the time on application.
These are 3 stacked series. 3 stacked series, so that's why.
The boot time incorporates the.
Yeah, this is the sum. What you see on top is the sum of the 3.
The sum of the 3, yeah. The boot time is the sum of all the 3s. Load time is creation and load, and creation is only creation. Well, and the red bars, of course, is the maximum execution time for this specific for 100 repetition for each image size. If we do the same experiment by launching code on the RPU, we see that they are very similar between each other. And what we can say here is that the time scale is the same, but there are a few differences. First of all, the creation time is faster. That's because we don't need to program the MMU for this specific virtual machine, because it don't have it. So it's faster. The load time is the same. But the start time is higher. Why? Because to start an RPU, so a remote processor, you have to communicate it with the firmware that itself communicate with the platform management unit. It's a core in the board that just is there for the platform management. And that core wake up the RPU. That is lower. It's 600 megahertz respect to the APU that's about 1.2 megahertz.
Where are you loading it from?
Loading it from memory. So before doing the tests, we take the image size of the virtual machine image and load from the SD card to the memory, and then all the tests is done with the virtual machine image in memory. So from memory to memory.
No content.
Memory to memory.
No
content.
And
This is a memory copy essentially.
Yeah. And finally, the boot times on RISC-V core on a soft core, we have the same result from create load time of the RPU, but in case of boot times, it's very fast, because actually in FPGA, the core is always active. It's just in reset mode. So to power on this core just means to take it out from the reset mode. So it's very fast, very precise. And it's a very simple code. The one that we deployed is called Pico32, and it's a very simple code.
Good question.
Yeah.
What do you consider boot time, since you're not starting operating systems or anything here? When are you done with boot?
Yeah, the boot times is the first instruction of the main of a bare metal application. So the first instruction just take a value of a system timer, and the difference between this time and the time when I started the process.
So there's always some DSP code that gets executed before the main. So that's what you're showing in the end.
Just so I understand the picture, I mean, I would thought that some of these things, you're multiplexing devices that are running an image, so can't you essentially quiesce or just snapshot or, you know, an image, and then the load time just goes away, so.
Yeah. Yeah, actually, yes, you can do all this stuff. Maybe the idea of doing this copy is basically to have the flexibility to change a runtime where you want to execute your code. Maybe you have this specific memory free, and so you decide to run this virtual machine.
Sure, no, I get that, but there is value in just doing the boot of an image that already exists, that's already in memory.
Pre-initialize, and yeah, makes sense. Yeah, you could do that, yes.
Yeah.
And like from a live snapshot, yeah, of course.
Okay, so another experiment we try to do is about spatial isolation. So this experiment, we want to demonstrate that if you don't use this kind of mechanisms that are transparently do through the Omnivisor, you risk to compromise the spatial isolation of applications. So to test this spatial isolation properties, we run a simple virtual machine under test, we call it, on the RPU and on our RISC-V. And while this application is reading and writing some metrics in a loop as a periodic application, we are trying to attack the specific area of memory the specific core is using by using other application on different cores. So for example, an RPU 0 is doing this application, while the RPU 1 trying to read and write the specific address where the RPU 0 is working in memory. What happens if we do this kind of work is that. Okay, I want you to focus first on the central image. The central image says we have a RPU running a virtual machine as we intended. The RPU 0 is running this virtual machine on the specific address in memory, reading and writing these metrics. And it do it at a certain rate. So it has a specific execution time. It's very fixed because the RPU is very precise. But after 2 seconds of execution, we start a disturbance algorithm on another core. In this case, in the central case, it's the RPU 1, so it's the other RPU. If we don't control it, we show that in this loading bar that the application crash. So we are able basically to make the core crash using another core. If we program the RPU, the MPU, the system MPU through the Omnivisor, what happens is that the application stops crashing, so it's going forward because the RPU is not able to access this memory, but we have some temporal interference. As we can see in this part of the graph, there are some temporal interferences, this red point and line that we see in the center. So this is temporal interference that we have. And the temporal interference is not locked in this case because the RPU is not a fast processor, but there is temporal interference. So if we apply also QoS regulation, we are able to have a straight line, basically no interference to the application running on RPU 0. This is the full Omnivisor. We repeat the experiment on RISC-V, having similar results, and we repeat the experiments using the FPGA and the APU as disturbance application. What happens in the FPGA is very, very similar to what happens in the RPU1. So we crash the application in the first case, we have some temporal interference in the second, and when the full Omnivisor is implemented, we don't have any kind of interference, temporal or spatial.
Can you guess why in the APU the RPU flow doesn't crash?
What happens in the APU is that actually it doesn't crash.
Sorry, why doesn't, it's because you still have the page tables and stuff, right?
Yeah, the APU already, the classical traditional hypervisor has the MMU protecting the memory. So when I create something in the other processing core in the system, what happens is that the MMU is going to crash the application, in this case Linux. Linux is trying to access the specific memory of the RPU, and the hypervisors just say, okay, you cannot do it, and the Linux crash itself. In fact, we have that, yeah, the execution time doesn't have, in the first case, so with traditional hypervisor, any kind of disturbance because Linux is crashed. So if instead we protect the area, Linux is continuous writing on the specific area, what happens is that we have a slowdown that is 2x respect to the execution, because in this case we have 4 application processing units very fast writing and reading from the specific memory. So we have this kind of problem. And I can show you more in detail the temporal behavior of the application. This is basically the same stuff, just focusing on the RPU executing this code. We know that the standard execution takes 80 80 milliseconds circa to execute. And in this graph, we show what happens if we protect from spatial point of view on the top, but not using QoS or any memory regulation. What happens is that execution times grow up through 200 milliseconds. What happens instead if we protect from both from spatial and temporal point of view? We have that the execution time has some micro spike during when the specific core starts, but something that we can be calculated and considered during real-time analysis. And finally, we do the same test on a bunch of benchmarks from Tackled Bench Suite that are simply binary search, fast Fourier transform, and other benchmark of this kind. And we can see the blue lines, that is traditional hypervisor in the sense that we protect the memory, but we don't have any kind of bandwidth regulation. While the orange one is the slowdown in case of using of the Omnivisor with temporal bandwidth isolation. Of course, we have to say something here, is that for this experiment, we use the bandwidth allocation as a maximum power possible. So we just going to throttling all the other cores in the system, so they are not going to use to interfere with the application. That's not obviously the optimal case, because we want to regulate the QoS to give a specific, for example, a wanted slowdown. I want a specific 10% slowdown maximum so that the other can do something in the system, actually. They are not completely blocked. And so this is the use case and future works we want to work on. And first is the integration of dynamic reconfiguration of this bandwidth application, this bandwidth regulation. There are some works on it. So the possibility to understand which kind of delay we want and program the QoS to have it. Then we want to provide a library of application virtual machine for remote processor to do some monitoring and managing a system for the managing for the entire board, because there are several research projects that use this coprocessor to do managing of the board, monitoring of the behavior of the other cores. So it's something that can be much more easily when you have an Omnivisor that can give you the possibility to launch this application and to isolate them, both spatially and temporally. And finally, we are interested into dynamic respawning of softcore. So the RISC-V that we have seen in this presentation is created at boot time in the system. But if we can, with the Omnivisor, not only launch a specific code for this softcore, but just changing the core or launching the specific softcore when it needs on the FPGA. There's something we want to discover and see if it is possible, actually. And that's all. So thank you for your attention. Sorry.
I got a quick question regarding your implementation. You mentioned all the different components that you put together to achieve your solution.
Yeah.
Since you're doing a PhD, what is your scientific knowledge behind this?
My scientific knowledge behind this. Okay. Well, the idea is that sense of yeah, of course, this is an integration of technologies, that's for sure. But this is something that has never been think about, like to have a single holistic software that can manage different kind of application, also with different ISA. That's something that doesn't exist yet. So imagine RISC-V, the RPU is ARM 32-bit, and the CPU, the APU are ARM 64. So the idea of an holistic software that manage all this ISA with a simple interface to the user, I think that's innovative thing.
So that's just surprising to me in the sense that, predating virtualization even, people built real-time systems. I thought they had various microcontrollers that didn't support virtual memory, etc. Did they not have mechanisms to isolate
Sorry,
them?
so
So
the answer, I missed the first part. The hypervisors.
forgetting about virtualization, but you know, I would have thought there'd be a lot of systems out there that did have specialized, you know, microcontrollers and stuff that would, and didn't they have to, don't they have controls out there to control which memory they can access?
Yeah, like RTOSs, they do program MPUs, of course, yes.
So then, in some sense, that is that ability to control these other devices always had to have existed, right? Here you're trying to put it into a common framework, but I'm just curious, like if you go back to what real-time operating systems have done, and they would call it launching a process over there. How does that differ what they have to do that?
Yeah, but remember, normally in a free like in a RTOS, what you're protecting is an application from accessing the memory of another application and from accessing the privileged memory, right? So for example, of the OS itself.
Right.
So there's always a focus on we are managing these resources to make sure that there's compartmentalization on the stuff that runs between the stuff that runs on the RPU. But the CPU as a whole, right? If it runs an operating system, for example, can be completely unconstrained when it goes and access requested. When you think about this processor in the bigger environment, which is a heterogeneous MPSoC like this one. So they're always focused on, let's compartmentalize things that run inside the OS, but the CPU as a whole, in terms of capability that it has when it puts an address on the bus, they don't worry about that way, right? Does that make sense?
No, I guess I would have thought that that they would have had multi-chip systems that where these more limited processors
Oh, I'm
were
sure.
still
Yeah,
running.
don't get me wrong. I'm sure there are bare metal solutions that absolutely use this stuff, right? But the question is, can you point out to a project that is self-consistent and being maintained, which try to address partitioning, temporal isolation of things that are cores, but also different ISA cores, as well as potential future core you develop on an FPGA. That to me is the kind of thing that the problem we are spearheading. Did I summarize correctly? I didn't feel the answer from you.
I guess I have a question about like, so how are you envisioning these kind of dynamic policies? Like, is there some use case where like something is running, you're thinking, oh, I might increase the QoS on something.
Yeah.
Like what is?
Actually, I think there is a better person that can talk about it.
No, you say.
But yeah, there are some words that follow exactly this. So there are some mixed criticality application in which maybe you can say, okay, this is a specific hard critical application. For now, I just let it run as it is, and I let the other application running the system as it is. Then I can monitoring the execution time, the status of this specific hard critical real-time application. So when this critical application is going to slow down for some reason, we are going to understand it, forecast this kind of behavior, and program the QoS and memory variable bandwidth allocation.
At that point, you would have to have some mechanism to monitor how the application.
Absolutely. And guess what? That monitor can be a virtual machine.
On RPU.
I see.
And the hardware.
And the hardware.
Yeah.
Depending